Okay, in this video we're going to learn about redox chemistry. Specifically, here are our three goals. We want to be able to explain the oxidation state changes to carbon atoms that happen during biochemical pathways. We want to be able to predict when NADH and NADPH are used and how they're biosynthesized. And then we want to be able to predict the effects of cellular perturbations on NADH and NADPH abundance. Okay, we're going to try to get through all that relatively quickly. So let's start with carbon. Carbon has a variety of oxidation states in biochemistry and biochemical pathways. So when we talk about oxidation states with carbon, we're talking about how many electrons are formally assigned to the carbon. So here's a carbon atom at the center of these bonds. This carbon atom is attached to four different groups. One alkyl group here, presumably another carbon, and then these three hydrogens. Now, each of these carbon-hydrogen bonds has two electrons in them. And because hydrogen is relatively electropositive, or it's less electronegative than carbon, formally we assign all of those electrons in the carbon-hydrogen bonds to the carbon. So in that sense, this carbon we would say is very reduced. Reduced meaning it has a lot of electron density. All of the electrons are really on the carbon. Because if we were to remove the hydrogen nucleus, the proton, the electrons left behind would now be associated with the carbon. That's how we think about it formally. So that's a fully reduced carbon, an alkyl carbon. A methane, for example, carbon with only attached to hydrogens is a fully reduced carbon. Alkyl groups, methane, ethane, propane, butane, those are fully reduced carbons because all of the electrons are associated with the carbon. Now, if we start to consider some oxidation, let's say now we have an alcohol. So now the carbon has one oxygen bonded to it, and we still have these other two hydrogens and the R group, like another carbon alkyl group. So in this case, oxygen is pretty electronegative, more electronegative than carbon. So we're going to assign those electrons to the oxygen. That means if we were to remove this OH group, this alcohol group, then the carbon left behind would not have these two electrons. It would be a positively charged carbon. So in that sense, this carbon has been oxidized. It has lost electrons. It would be fairly doable to remove those electrons by removing the hydroxyl group here in the form of hydroxide, for example. So as a carbon atom is bonded to more oxygens, it becomes more oxidized. The electrons are increasingly associated with the oxygen and not with the carbon. So an alcohol here is more oxidized than an alkyl group. If we just think of the R here as being a hydrogen for simplicity, then we would say that methanol is more oxidized than methane because we've got one oxygen attached to the carbon, whereas in methane it's all four hydrogens. We can go up one more level of oxidation. So what if we have an aldehyde? An aldehyde has a carbon that has a double bond to oxygen. So the oxygen now has two bonds to the carbon. So again, another pair of electrons, two more electrons, are now associated with the oxygen. So the carbon is becoming more oxidized because more of the electrons are associated with the oxygen and not with the carbon. So again, if we think about the simple case where R here is, the R group is just hydrogen, H, then this would be formaldehyde. Formaldehyde is more oxidized than methanol, which is more oxidized than methane. And then we can go all the way to the carboxylic acid. So now we have this carbon atom attached to three oxygens. One is through the double bond to the carbonyl, and then this other oxygen. So that's all 6 of these electrons, and each bond has 2 electrons. All 6 of these electrons in these bonds, these 3 bonds, are associated with the oxygen formally. So the carbon is becoming more and more oxidized. Fewer and fewer electrons are associated with that carbon. And again, if R were H, hydrogen, then this would be formic acid, and so that's more oxidized than formaldehyde, which is more oxidized than methanol, which is more oxidized than methane. And now we go all the way to carbon dioxide. So carbon dioxide, the carbon has 2 double bonds to oxygen, and it's fully oxidized. That's a complete oxidation of carbon, because all of the electrons in these 4 bonds, these 8 electrons, are all associated with the oxygen. None of them are associated with the carbon. So we would say now this carbon has been completely oxidized. All of its electrons have been stripped off, formally speaking, by being associated with the oxygen. So this is the series of going from more reduced. An alkyl group is the most reduced, with just hydrogens associated with the carbon, then an alcohol, then an aldehyde, then a carboxylic acid, and then carbon dioxide. And if you forget that order and you want to check, you can just count how many bonds between the carbon and oxygen. If it's 1, 2, 3, or 4, that will tell you the more bonds to the oxygen with that carbon, the more oxidized it is. Now we can look at the example of glucose in glycolysis and metabolism. Glucose, let's look at the structure for glucose. Here's the structure written out in the chair form, the cyclic form. But if we just write out the molecular formula, we have 6 carbons in glucose, 12 hydrogens, and 6 oxygens. So effectively, every carbon has 1 oxygen associated with it. It's substituted with 1 oxygen per carbon. So that's like an alcohol. A sugar like glucose is effectively like an alcohol in terms of the oxidation state of carbon. It's actually fairly reduced. I mean, there is 1 alcohol, so it's more oxidized than if this was just, cyclohexane, but it is relatively reduced compared to these other kinds of species. Now, when we go through metabolism, the carbons in glucose end up being converted to carbon dioxide. So that's the complete oxidation of carbon. You can see that the carbon, each of these 6 carbon atoms is going to end up as a CO2 molecule. So each carbon is getting fully oxidized, going from this more reduced form, the alcohol form here in glucose, to the completely oxidized form. So metabolism, glycolysis, TCA cycle, is a way of completely oxidizing glucose or sugars. And so again, when we go in the leftward direction here, we're reducing carbon, and we go in the rightward direction, we're oxidizing carbon. And metabolism in the glycolysis, for example, in the TCA cycle, we're going in this direction of oxidation. Okay, so that's about carbon. Now what about the use of NADH and NADPH? Now these are very related to oxidation state because they're used to oxidize and reduce carbon atoms, often ketones and alcohols. So for example, let's look at an alcohol and an aldehyde. So let's say we had an alcohol such as ethanol. Well, we could oxidize that carbon, imagine oxidizing it, to make it into an aldehyde. So it's becoming more oxidized as we go to the aldehyde, because now we've got 2 bonds between the carbon and the oxygen versus only 1 bond in the alcohol to the oxygen. So we're oxidizing as we go to the aldehyde, and we're reducing the aldehyde when we go back to the alcohol. And so those are the reactions that are facilitated by NADH or NADPH and NAD plus or NADP plus. So NADH and NADPH deliver 2 electrons to reduce this aldehyde to the alcohol. NAD plus and NADP plus, the oxidized form of these cofactors, do this oxidation, the reverse reaction. They remove 2 electrons, transferring them onto NAD plus or NADP plus to make NADH or NADPH, and then the carbon gets oxidized to the aldehyde. Okay, so again, if you're doing an oxidation of an alcohol to an aldehyde, what are you going to need? You're going to need a place to put those 2 electrons that you're taking away from the carbon, and you're going to do that with NAD plus or NADP plus. If you're reducing a ketone or an aldehyde to an alcohol, you're going to have to deliver 2 electrons, and that's going to be with NADH or NADPH. Now, where do NADH and NADPH come from? NADH is usually synthesized through catabolic pathways, such as glycolysis and the TCA cycle. If you look at the TCA cycle in particular, there are 4 points where these reduced cofactors are generated. 3 places where NADH is generated, and 1 place where FADH2 is generated. So as we go from a 6-carbon citrate down to a 4-carbon succinate, that involves 2 oxidative events, and each of those generates an NADH. Now, as citrate, which is fully reduced at the 2 central carbons, as citrate gets oxidized up to oxaloacetate, you can see that we're adding a carbonyl here, a ketone. So this carbon, the 2nd carbon, is getting oxidized. It's going from CH2 to CO, to a carbonyl. That means we're going to have to do some oxidation. We're going to need to generate NADH and FADH2. And so in this set of reactions, because we're oxidizing that carbon, we're using FAD to make FADH2 and NAD plus to make NADH. In other words, we're transferring these 4 electrons from succinate onto these cofactors, generating the reduced form of these cofactors. We can look at that a bit more schematically, just thinking about the TCA cycle. We're generating NADH in these first 2 steps. In the last few steps, we're generating FADH2 and NADH as we reoxidize succinate to oxaloacetate. Okay, so that's a way that NADH is generated. Glycolysis and the TCA cycle are oxidizing glucose completely to carbon dioxide, and in the process they're generating these reduced cofactors, NADH and FADH2. That's a main source of this reduced form of NADH in cells. What about NADPH? Well, NADPH is a little different. It is synthesized by a different process, by the pentose phosphate pathway. So it doesn't come from catabolism like NADH does. It comes mostly from the pentose phosphate pathway. So how does that work? So glycolysis in the TCA cycle, I just said, are oxidizing glucose to carbon dioxide and generating NADH. NADPH is coming from this shunt pathway called the pentose phosphate pathway. So that is a different fate of glucose 6-phosphate. Glucose 6-phosphate can either continue down glycolysis, or it can go into the pentose phosphate pathway where it makes 6-phosphogluconolactone, this lactone, and then goes on to various fates. But this is the key reaction in terms of NADPH, because this is an oxidation of glucose. Glucose is getting oxidized. You can see, looking at the lactone structure here, this carbon with the carbonyl, with the carboxylate here, the lactone carbon, has been oxidized. Normally that would in glucose be an OH here, and then we'd have the cyclic form, but this is now oxidized to the level of an ester, or a cyclic ester, a lactone. So in this oxidation of glucose 6-phosphate to the 6-phosphogluconolactone, to this lactone, NADPH is generated. It's the place where the 2 electrons from this oxidation are stored. NADP plus goes in and NADPH comes out. Now the enzyme that catalyzes this is glucose 6-phosphate dehydrogenase. Dehydrogenases are enzymes that do these kind of redox chemistry reactions and usually generate or use NADH or NADPH. So in this case, NADPH is being generated by this enzyme, and we need this pentose phosphate pathway in order to generate NADPH as the main source in most cells. So interestingly, individuals that are deficient in glucose 6-phosphate dehydrogenase, in other words, that can't make NADPH, this major source of NADPH, as we would expect, have low levels of NADPH. So they're deficient in NADPH. And what happens to them? Well, NADPH, I said, it's a reducing agent. It provides electrons for reduction reactions, and it's the major source of eliminating oxidative stress, so-called oxidative stress, oxidative damage in cells. And so individuals that are deficient in making NADPH because of this G6PD deficiency are now ultrasensitive to oxidative stress, particularly in their red blood cells. Okay, so to summarize, in this video we learned how to recognize the oxidation state of carbon, where NADH and NADPH are biosynthesized, and the role here at the end of NADPH in countering oxidative stress.